Yes, let's learn about coils, shall we? Yes, with the Frankenstein lab out in the old garage. Come on. Let's figure that out. Hey there. Welcome out to the old whiteboard at the garage. Let's talk about a coil of wire. Okay, I'm going to draw a coil of wire here on the board. All right, so it's just a loop of one piece of wire. And when we apply power and ground in a circuit, okay, and if let's say that I send 12 volts through this circuit, and that this coil of wire is going to pull 2 amps of current. When I do that, it's going to generate a magnetic field. Okay, it's going to generate a nice strong magnetic field within that coil of wire, and at that point we can use that magnetic field to move something. We can use it to move a solenoid or a pintle or an arm on a relay. And you know, this 12 volt signal would be sent from the computer. Probably it would always have power on one side. The ground would be controlled from within the control unit inside the computer. If we take a look at our old friend Ohm's Law, all right, E over I times R, okay, and we figure this out. If I take the E is the voltage, 12 divided by the current, I put my hand over the R, I'm going to solve for resistance. If I wanted to know the resistance of this, and it's drawing 2 amps, so we'll put the I down here. This is my 2 amps. The answer is it's going to draw 6 ohms, or it's going to have 6 ohms of resistance. Now, Ohm's Law, we know, lies sometimes, but just stick with me for this example, because we're gonna damage this coil. We're gonna break it, okay? And we're gonna explain why broken coils don't work the way they should, okay? So the computer that's controlling this expects to see 2 amps of current pull to generate proper type of magnetic field to do something. Move a fuel injector open, that oil control solenoid, okay, works that same way as well. So we're going to pull that back when we have that magnetic field. We're going to let that oil flow. We're going to let that fuel flow through that system. So ideally, okay, when this thing is good, so I'll write up here the good one, okay, when it's good, we have a strong magnetic field. Our resistance is going to be 6 ohms, okay, and our current, well, I'll use I rather than A for amperes. I'll use an I. Our current is going to be high. It's going to be 2 amps. Okay. Now let's change the game a little bit here. Okay. We're going to keep the voltage the same because the computer really is always going to be sending out that same amount of current. But let's change the resistance of this thing. Okay. Let's have a broken coil. So if there's a break in this coil of wire, what that means is that there will be no magnetic field generated, and that's because there's no way for this to be a complete circuit anymore. So the magnetic field within the coil, because the coil now has a break in it, here's my break, okay, right there, there is voltage, but the fact is there's no current. And if there's no current flow through the coil is not going to generate any magnetic field. Okay, so we call that an open circuit. All right, so with that open, I'll start writing down here an open, O-P-E-N, and gosh, this is hard to draw on the side. An open circuit equals no magnetic field. Okay? And if we wanted to figure out the resistance of this, well, the fact is if my current is 0, okay, that means my resistance, because you can't divide by 0, kids. Remember math. You can't divide by 0, or at least you're not supposed to. The fact is that my resistance is infinite. It's an open circuit. That break could be a mile long. It doesn't matter. The fact is at 12 volts, I'm not going to get electrons to jump across it, which means that there's no magnetic field. Okay, my resistance is very high. It is in fact open. Okay, it's infinite resistance. Okay, and my current is going to be 0. There's no amps flowing across that. So that's a broken coil. What do you need? I need a new coil at that point. Now, what caused the break? I don't know. It could be heat. It could be vibration. It could have been some type of mechanical fault on the inside of the coil that caused it to fail. Okay? By the way, this is how everything's a coil of wire. I don't care what it is. I don't care if it's an ignition coil. I don't care if it's a heating coil. I don't care if it's some type of magnetic pickup and a sensor for an ABS system. It's all the same stuff. I mean, this could be a light bulb. It's a coil of wire. Right? It doesn't matter. However that works. Okay, so now we're back. We're back again. All right, let's erase our probability here. So there's another one, and this is good, right? Got good resistance, good current pull. An open is no magnetic field. It's broken. And that's tricky because you don't know if it's because of the connection, if it's the power of the ground or the coil, and that's where people guess. And you don't ever want to guess. Don't be the person that guesses. So the last probability that we have is a short, and a short is when I fuse together multiple sections of the coil, which means the overall resistance now skips those coils in the middle. Okay. And what that's going to do is if the resistance goes down, so if you remember my good coil there was 6 ohms. It was 6 ohms. Let's say that my resistance, by having it go down, because I have a short and I'm bypassing those other sections of that coil, it's now not 6. Now my resistance is 2 ohms. Whoops. We got to change our formula here, right? So if I want to find the current now, what I'm going to do, gosh, what is all over my poor board? Anyway, if we want to find out, and we know that there's a short with this thing, okay? If we take the resistance, and my resistance has gone down, and let's say that my resistance is now 2 ohms, and I want to find out the current. Well, now when I divide 12 divided by 2, so I'm going to try to solve for the current now. What that is if I put my hand over the I take the 12, which is the voltage, my lower resistance because of the short, okay? And what that comes out to is that means that now, instead of drawing 2 amps, which was a healthy system, I am drawing more current than I should. I'm drawing 6 amps. Now here's the crazy thing. You would think that because of the higher current pull, maybe the magnetic field is stronger, but here's the thing. The magnetic field is weaker because it's canceling out these coils. It's not taking advantage of them. So the magnetic field in this entire thing is very weak. It's nowhere near what it was. So a short in a coil equals a weak magnetic field. Okay? It equals a weak magnetic field. The resistance is going down because it's a short. It has less resistance because we're canceling out those other coils. So the resistance is low. And that means that my current is actually going to be higher. So this is one of those things where you go, but it's a weaker magnetic field, but the current, well, see, you have to understand the theory that the fact that it's pulling more current is a sign that this is shorted. Now, normally in some situations, if there was a fuse on the circuit, we might keep blowing the fuse. Well, if I have no shorts in my power ground side, that would tell me that the short is shorted internally. Now, there's multiple ways that we can measure this. We can measure it with a meter or a current probe preferably. But, you know, when we're talking about coils, just remember it's only ever going to be one of these three scenarios. It's either broken and open, okay? It's shorted internally, which means it has a weak magnetic field, in which case it's going to pull more current than it's supposed to, or it's good, which means it works. That's pretty much it. Okay. So, being a good diagnostician, one of the things that can happen with a coil is that its temperature will change. As it's good and cold and strong and has a good magnetic pull, what is going to happen with this thing is that as the temperature of this increases, if you remember one of the basic rules of electricity, is that as the temperature of an object goes up, its resistance goes up as well. Okay? There is a chance that this resistance will start to go up, and as this thing warms up, maybe it's actually 12 ohms. Which means that if we come back to our friend Ohm's Law here, let's say the coil is overheating, it's getting too hot, and the resistance is going up. If we come back to our old friend Ohm's Law here, okay, and we want to figure out now the amount of current that we have. If I put my hand over the eye, and I now have 12 ohms when this thing's hot, 12 ohms, that means that this is only going to draw 1 amp of current, which means that it's going to weaken. It's going to get weaker as it gets hotter. This is the tricky one, because if you have a situation where, well, when it's cold it works, but when it's warmed up it doesn't, that's what's going on. There's a short inside that that's hard to detect, but that's what's happening is as that coil warms up, it starts to fail. Okay, I think we covered that sufficiently. Let's move on. Okay, so over here on the Mini has 2 variable camshafts. So the oil control solenoids for this guy, there's one here, down here. It's literally solenoid. It's held in by a bolt. Take the bolt out, you slide the whole solenoid out. Has an electrical connector. There is another one located at the rear. That is this guy right here. That's the other oil control solenoid. So both the intake on this car is in the back, and the exhaust cam in the front are variable on this car. On this, the exhaust cam here, remember that the exhaust is on the turbo side. This is my feed line to my brake booster, so it also has a cam-driven vacuum pump. And then on the intake side, that's where they put the high-pressure fuel pump on this. Okay, there are 2 camshaft sensors. There's one here and there's one here. So this car both controls the intake and the exhaust camshafts are variable. And then we have 2 sensors to monitor where those camshafts are positioned in their phases. If there's a fault, either with oil pressure or valve timing chain in here is not known to be very good quality, unfortunately. Anyway, it would set a check engine light. Yeah, so that's where that stuff is.